in this table here is the total depth for that particular duration. So in our case, we're gonna look at a 25-year storm, and for this location, for 24-hour duration, that depth is 7.97 inches. So that's the total rainfall for that 24-hour period. Does that make sense? Okay? So for your pond, we're looking at 2 storm events. We're looking at the mean annual storm, and we're looking at the 25-year, 24-hour storm. So the mean annual storm is a 2.33 year frequency with a 24-hour duration. And for that one, you want to make sure the post-development discharge is less than or equal to the pre. So post is proposed, pre is existing. For the 25-year storm, same thing. Q post is less than or equal to Q pre, but this is the one where you're also going to look at the peak stage. We talked about the peak stage being a foot below the top of bank, so you have 1 foot of freeboard, okay? So going back to the NOAA Atlas, if you notice here, there's a 2-year storm and a 5-year storm. There's not a 2.33-year storm. So your task is to figure out what the point rainfall is for a mean annual storm. So hopefully you can use some math and interpolations from thermodynamics or something to figure that out. So, okay? So rainfall, hopefully that's clear. Okay. The other thing that I did is I uploaded a rainfall distribution, and we're going to use the SCS Florida Modified, which is an SCS Type 2 rainfall distribution, which is modified for Florida. And this table here gives you the ratio of rainfall for 24 hours, and this is on half-hour increments. So by hour 24, that factor is 1, which means you had 100% of the rainfall, right? So this fraction here, or this decimal, is the fraction of that total rainfall. So in the example that I showed you here, we have a rainfall of, let's say, 8 inches, okay? So if I look at this distribution, I'm gonna take that 8 inches and distribute it from hour 0 to hour 24. So at hour 0, I have 0 rainfall, right? And then at hour 24, I have 8 inches of rainfall. So this will be important when we do PondPack, because you're gonna need to put this into PondPack to distribute the rainfall, okay? Hopefully you saw something like that in hydrology, but if you didn't, that's not a big deal. So anyways, I loaded this onto web courses. You should have that, okay? All right, so the other thing I wanted to highlight before we get into PondPack. The first is, I didn't mention this specifically last class, but the Weir equation, hopefully you all have seen that. It's flow times the Weir coefficient times the length of a weir times the head, okay? So this is what you're thinking about when you design your outfall structure. So again, the length is directly proportional to the flow. So if my length gets bigger, my flow gets bigger, right? If the length gets smaller, the flow gets smaller. So again, when you're trying to meet this Q post versus Q pre, you need to think about that as you're running your pond, okay? So the other part that I wanted to highlight is talk about the control structure in this orifice. So I really didn't give you any guidance on how you're going to design that orifice. I wanted to highlight that right now. So again, what's that orifice doing for us in the pond? What's its purpose? Primary purpose.
Maintain normal water level.
Yeah, it's maintaining that water level, okay? Its secondary purpose is if you think about a wet detention pond, what do we want in a wet detention pond? What do we want to maximize in a wet detention pond within that permanent pool or that water? What do we want to happen? We want it to take a long time, right? We want to hold it back and slow it down. We want to try to stretch that out, because the longer we stretch that out, the more treatment and removal I'm going to get, okay? So we don't want, when we have a storm event, we don't want it all just rushing out of the weir, right? So once we get rid of the flood attenuation, we want it to bleed down slowly through this orifice so we maximize the amount of removal that we get, okay? So what we want to do is be able to size that orifice so we achieve the 14-day recovery time, okay? So what we're gonna do is we're gonna look at the orifice equation, which is here. The flow is an orifice coefficient times the cross-sectional area of the orifice times the square root of 2gh. G is just the acceleration, or 32 cubic feet per second squared, and h is the head. That's the head on the orifice, okay? So we want to be able to solve this for A, right? So A is the area of the orifice. That's what we want to try to figure out. So that's just Q. So we want to be able to solve for that. And our orifice is circular, so that's just pi r squared, right? So if we can solve for R, we can come up with the size of an orifice, okay? So how do we get these things? This is a coefficient, and standard orifice coefficient is 0.6. G, we already said, was 32.2 cubic feet per second squared. H is the head. So what we're going to look at is the average head. So it's really the height of water above the orifice. And what's happening over time to this head?
Decreasing.
It's decreasing, right? So if we use this value, we're probably overstating it, right? So if we use an average, pick a point that's in the middle, that's probably fair, okay? So if this was elevation 98 and that was elevation 96, then this is 2. So if I wanted to use the average, I would use 1, right? So that's how to do that. So the question is, what is Q? So Q is just volume over time. Okay? So what we want to do is vacate this volume between the weir and the orifice in time. And we want to do that in 14 days. Okay? So do I know this volume? Anybody?
Yes.
Right? You do, right? Because you have a stage, area, storage relationship for your pond. So I can calculate this volume, right? You agree with that? So if I know that volume, I know my time, I know flow. So if I solve this for A, I can come up with a radius, okay? And then that would define the size of the radius. Does that make sense? Now, when you do this, you may get, yeah.
So the volume would be the rectangle area times the.
Not exactly. So it's, the cross section of your pond simplistically is like that, right? And so let's say you're talking about this slice within the pond. So, so it's not exactly the depth because you're at an angle here. But you can do the average end area method, like what we did in class, so you can figure out what that volume is. Okay? So when you, when you solve for this, you might, you'll get a radius of something, whatever. Let's say you solve it and your radius is half an inch. Actually, let's say it's 0.47 inches. Okay, so that's a radius, so that would mean the whole orifice would be, in diameter, would be, almost an inch, right? Now, St. John's has a requirement that that orifice has to be at least 6 square inches in area. So if you do a quick calculation, you can figure out what that diameter is. if you come up with a diameter that's less than 6 inches squared, you need to use this diameter. Okay? So if you do this calculation, and you get some small number, you have to use this dimension here, okay? Why do you think that is?
Factor of safety.
Yes, it is a factor of safety, but why? So let's say that I do this calculation and my orifice diameter is 1/2 inch. Let's say that's the size, that's the diameter. That's that big, right? Maybe? What's gonna happen like in 4 days? It's gonna get clogged, right? So you wanna make it big enough so that you have that factor of safety, because you still wanna be able to vacate the water, okay? So if you calculate something that's that small, you wanna go ahead and use that value, whatever that diameter turns out to be, okay? Now, if you get something that's larger than that, that's fine, okay? But if you get something less than that, you wanna use this number. The other thing I wanna tell you too is think too about somebody has to build this, okay? So if you do this calculation, and let's say you come up with 3.61 inches. That's 3.75 or 3.5, keep it simple. If you make it that, the contractor's probably not gonna build it to that, so try to use something that's reasonable when you do that, okay? Does that make sense? Any questions on the orifice? Yeah,
So if the orifice is less than 6 inches
squared.
squared,
Cross-sectional area,
then use 6.
yeah, you wanna use that.
If it's over 6, then use whatever's over 6.
Right. But again, that's an area, not a diameter. So I'll allow you to calculate what that diameter would
Okay.
be. Okay? Anybody else? Okay. So now we have new, you're gonna get this, would you like to create a pre-post development analysis scenario? Just say no. Okay? PondPack is similar to StormCAD in that it's a nodal kind of layout. So you're gonna graphically lay out things, and then you're gonna put in data, much in the same way you did with StormCAD. So all of these Bentley programs kind of are set up with that same user interface. Okay, so the first thing we want to be able to do is we want to be able to define our pond. And there's some icons here, and the pond icon is this thing that sort of looks like a pond. So if you click on that, you're gonna get this icon. You can see that looks sort of like a sick pond. But what you wanna do is you wanna click 4 corners, okay? And then right click and say done, and it'll create you a pond, okay? And then what we wanna then be able to do is we're going to go up here to this little nodal thing and click pond outlet. You're gonna click that. Okay, and then you're gonna right click and click outfall. So we just put in this pond outfall entrance, and this is where we're gonna define the outfall structure, okay? And then this outfall is literally just the outfall, which would be the wetland or Lake Claire or something like that, okay? So what we're gonna do is we'll also need a catchment area. So we need to know what that area is, that basin area that goes to the pond. So if I click this icon, that's the catchment area. Again, much like in StormCAD, just draw on a rectangle with 4, and boom, I got a catchment area. Okay? So now what we want to do is connect things together. So let's start with our catchment area. So if I double click on that, basically, what are the things I need for the catchment area? What pieces of information do I need? What 3 pieces of information do I need?
Time concentration.
I need a time of concentration. What else?
Velocity?
What's that?
Velocity?
Not velocity.
No.
CN.
We need a curve number. And what else?
Area.
Area. So we need those 3 things. So if I come here, the first thing, which we didn't mention, is it asks for an outflow node. Right now it says none. If I click in there, I'm gonna select outflow node. And the outflow node for a catchment is the pond. So if I click on the pond, it's connecting the catchment to the pond, just like in StormCAD, where we connected the catchments to the inlets. Then, if I come down under the runoff section, this is where I'm gonna put in my area. Okay, so whatever that area is, in our case, it's roughly 10 acres, right? And then it asks for a curve number. So you all calculate a curve number for your pre-development, post-development. So in this case, I'm just gonna say my curve number is 80. And then the last thing, it's asking for time and concentration in hours. So let's say it's 0.2 hours, okay? So that's our input for the catchment area. So with that, we now have all the information we need for that, okay? The next thing we'll do is let's double click on the pond. And for the pond itself, we just need to be able to define the volume. So the stage area relationship for the pond. So if we come down, that's not what I wanted, I'm sorry. Oh, volume, sorry. So under volume, here it says no volume. If I click that, I have some options here as to how I can define the volume. What you want to select is elevation area, okay? So if I click in there, click these three dots, it's gonna pull up a table. This is the table we did in class, right? So here I can put in elevation 100 and my area, let's say it's 2 acres, then 99, 1.9 acres, 98, right, you get the picture. So then, let's say we'll put in 96 and 1.5 acres. So that defines the area elevation information for the pond. That's how I'm gonna generate my volume, okay? So I've got that defined, okay? The other thing I wanna define is the actual outfall structure itself. So if I go up here to components, I'm going to define what's called a composite outlet structure. So I click on that, and I click on composite outlet structure. This is where I'm going to define these things. I'm going to define this weir, and I'm going to define that orifice. So it's a composite because it has a weir and an orifice. It could have 2 weirs, it could have a number of different hydraulic elements, but we're gonna do a weir and an orifice. So for that, if I right click under add, I'm gonna add a weir, okay? So the weir is gonna ask for a few things. Elevation. So what's the elevation of my weir? Let's say it's elevation 98. And then it's gonna come down here, and I need to define the shape. So I'm gonna say it's a rectangular weir. And then the last thing I need to put in is the length. So let's say my length is 2 feet, okay? So for the weir, elevation, geometry, and then the length, okay? And that will define the weir. Then if I want to define the orifice, I come back up to this composite outlet structure, right click, add orifice. And then the same kind of thing. So the elevation is that elevation of the normal water level. So in this case, I'm going to say it's 96. And then down here, it's going to ask for a diameter in inches. So let's say it's 3 inches, okay? So I've defined the weir, and I've defined the orifice. Any questions on that? Okay. Okay, so then if I click on this POE, which is the pond outfall entrance, I need to do a couple things here. The first is under pond outlet, I'm gonna click that, and I'm gonna select the pond, so it can connect it. Actually, that's all we have to do for that one. Then the last two more pieces of information, under the outlet, if I click that, it says has control structure, yes, composite outlet structure. I need to click in there and then connect the outlet structure I just defined. So it's now connected that to that, okay? And then the last thing is the outfall itself. You shouldn't have to make a change. We're gonna assume that it has a free outfall, but you could put in a rating curve, you could put in a static elevation, you have several choices there. But for simplicity's sake, we're gonna assume a free outfall. Okay? So what the program will do is it'll use Manning's equation and come up with the depth. But okay, so now we've defined all of the sort of physical elements of the system. We've got the catchment, we've got the pond, we got an outfall structure, and then we got an outlet. So all those pieces will work together. Okay? The next thing we need to do is define the storm event itself. So if we go up to components, and there's gonna be two pieces of data, storm data and then global storm data. So under storm data, we have some options here as to how we wanna give it rainfall data. So we could do a time depth, intensity, IDF curves, we can do equations, we got a lot of choices. But up here, under this little white piece of paper, we're gonna do time depth. And this time depth is going to be the distribution of the depth of rainfall over the 24 hours. So I'm gonna do a new return event, and I'm just gonna label my curve as FLOMOD, Florida Modified. It's a 25-year storm event, and where it says depth type, you wanna click cumulative, so it's adding up the flow as you go along. Start time is 0 hours, increment, I'm gonna use a half hour, and I'm gonna end it at 24 hours. So this kind of sets the parameters for our rainfall distribution. So now I have this table. And so this table will be based on the ratios that I showed you before we started. And you're gonna put in the incremental depths of rainfall from 0 all the way up to your total depth at 24 hours, which in the example I showed you was 8 inches. So you're gonna start off at 0, and then using those ratios, it's gonna be like 0, 0.1, 0.2, build up, and by the time you get to hour 24, it will be, in this case, 8 inches. Does that make sense? Anybody have questions on that? So what I would do, I'll answer your question in 1 second. What I would do is take that PDF that's uploaded, create a spreadsheet in Excel, figure out the ratios, and then you can distribute your rainfall, and then you can put it in. Did you have a question?
Which reference document was it?
It's called SCS FL MOD rainfall distribution. It's a 1-page PDF. And it should have today's date, so hopefully that helps in terms of finding it. If you can't find it, let me know. Okay. Then the very last thing we have to do is under components is go to global storm data, and then under global storm data, pick the storm event. And then that's it. So with that, we should be able to run this, okay? So I set one up already, and I'm gonna run it. And when you run it, you'll end up getting a table that looks something like that. And this is good to take a look at things and see how things are looking. So for this particular example, my peak outflow from the pond is 1.24 cubic feet per second, so that's pretty low. The inflow is 39 cubic feet per second. So this pond that I have is holding back a ton of water, okay? So, you know, I could probably make the pond smaller, I could probably, you know, mess with the weir, that kind of thing, okay? The other thing you can do in terms of output, there is a report and a report builder. And in the report builder, you have a lot of options of what information you can produce for a report. And you don't need all this stuff, but for the purposes of presenting it in your report, what I would like to be able to see is your rainfall distribution, okay? And then the pond stage time information, and then your what was it, time versus elevation, and your hydrographs. So I just want to be able to see rainfall, the pond information, stage versus time, and then your hydrograph, and then this, there'll be a summary table as well that you'll print out. Okay? Any questions on that? Yeah.
Is there a maximum peak flow?
Yes. So, what you can do, or what you will need to do, is you also need to run this for a pre-development situation, okay? So I can set this up in the same model to also do a pre. So what I could do is I could define a catchment, and then I can create an outfall and then just connect the catchment to the outfall. So in the pre-development condition, you're not routing it to a pond. You're just estimating an area, or a flow from your catchment or your basin area. So if I just connect the catchment directly to the outfall, I can do my pre-development in the same model, okay? So if I do that and I run it, I can see the relationship of the post-development or pre-development on the same table. And I can very quickly assess, am I meeting this criteria? Okay? So, again, what you want to be able to do is make sure that your post is less than your pre for these two storms. You want to make sure your peak stage is a foot below your top of bank, okay? So the variables that you have to work with are going to be the pond, right? You can make the pond bigger or smaller, and the outfall structure. So remember again, with the outfall structure, it's governed by the weir equation. So the longer my weir, the higher the flow. Shorter the weir, lower the flow. And the lower the flow, higher the stage. Higher the flow, lower the stage. So you gotta balance those. Okay? So any questions on what we've done? Yeah,
Where do you see your peak stage elevation?
say that again?
Peak stage elevation?
Where will you see it?
Mm-hmm.
Is that what you're asking? So if you, when you run it, you can see it a couple ways, but if, hold on. So when you run it, you'll see this table here. And if you look at your pond, here's the peak stage right here. Maximum water surface elevation.
And what would be a normal flow in and flow out where you're like, okay, that's not, it's
Well, that's a tough question to answer. But what I would tell you is, if your inflow is 100, 200 cubic feet per second, you've probably done something wrong, okay? that means that you've overstated your basin in some way. Something went awry, okay? So you saw this for 10 acres and a curve number of, I don't know, what, 70 or 80, and a time of concentration of 20 or 30 minutes. The flow is 39 CFS. So, gives you some order of magnitude. In terms of outflow, I mean, again, you're trying to meet this criteria. So there isn't really a set answer for you. But what I would say is, from a design standpoint, you want to try to make your post-development flow as close to the pre-development flow as you can. Why is that? What's that? Cost, right? Because I don't want to have a pond that's bigger than I need, because in the world of development or infrastructure, number one, if for a private subdivision, what's key is how many lots or how big a development can I get. So I want to make my pond as small as I have to, right? And then the cost of building it, right? So the bigger my pond, the more material I have, the more time it takes to construct. So I want to try to get my post as close to the pre as I can. The other thing is you want to try to get the stage as close to that 1 foot of freeboard as you can. This is from a design perspective. So again, you're trying to maximize the efficiency of your system. So if you have it like the case I have here, where the outflow is 1.2 cubic feet per second, you know, that's probably too low. And I might need to make an adjustment to try to maximize my design. Does that make sense? Everybody ready to design a pond? Any questions? All right, so we'll switch gears if that's okay.